is more curve sketching. This time let's find a hole with these problems. So we're going to factor first. So x plus 5, x minus 2, and on the bottom we get x plus 3 and x minus 2. So we have some canceling there. Remember, anytime we cancel, that's our hole. So x plus 5, x plus 3 is our new algebraic expression, our new rational expression. So let's verify that in the calculator. So I've got them plugged in, the first and the second. And so when I graph it, you should get one in blue and the other one perfectly tracing it in red. And so to see the hole, if we hit trace, you can see now it's blinking in blue. So if I hit 2 and enter, nothing appears. So now if I hit trace and select the red and then hit 2, it gives me 7/5. So that's what a hole represents, is that there's actually no point there at 2 7/5. It's empty. It's undefined, undetermined. Trace 2, enter, see, nothing. So we have a hole. We have a hole at the number we canceled, which is 2, but we still need to plug that in. So if we take our new function, right, we're going to call it g of x now. This is the one we're going to be using for everything. We can now find g of 2. And so 2 plus 5 over 2 plus 3 is 7/5. And that can check in your calculator. Remember, I plugged it in and it said 7/5. So now what's left is our vertical asymptote. So we're going to get one at x equals -3. Let's put that in red. Let's put them both in red. So 2 7/5, x equals -3. So we're going to go 1, 2, 3, vertical line. And then 1, 2, and then 7/5 is 1.4, so it's between 1 and 2. Right there. Oops, it's not a dot. It's a hole right there. So at 2, 7/5, and we know what our graph looks like. So it's going to come down like that through there, and so I can put it on top to know I'll avoid it. So now we just need to take our first derivative and to write our domain. So our domain here is x cannot equal those two numbers, so -3 and 2. The first one is a vertical asymptote, the second one is a hole, and there we now have our graph. So now let's see if there are any local extrema, and we're not going to be using this function anymore. It's already been simplified, it's here. We've placed the hole, it's taken care of. These are the same functions, except this one, we'd have to add our removable discontinuity here. So over here, we're just going to put a little x cannot equal 2, okay? And then that gives us our hole. So now we come down here and we go g prime, and we're going to take the derivative. So this is a quotient rule. So the top is x plus 5. The bottom is x plus 3. And so we would get g prime of x is equal to, and then that would be 1, x plus 3 minus, and then that would be 1, x plus 5 all over the denominator, which is x plus 3 squared. And so this would give us x minus x, which is 0, and 3 minus 5, which is -2. Okay, so we found our g prime of x. Now let's find our critical numbers, and there aren't any. So remember, the bottom here is a domain no-no. So all we have to do is worry about the top, and there's no way the top is going to equal 0. So we just go back to our domain, and we're going to put a red line at -3, and we'll even do a vertical, and then 1 at 2 with a hole. So our graph is being cut up into these intervals. So we're not going to get any relative extrema because we did not get any critical numbers. But we are going to get is increase and decrease. So we still need to find those by plugging them into our function. And if you look at it, it's negative over a positive. So no matter what you plug in here, -100, you're going to get negative over positive, which is, you guessed it, negative. So it's decrease. And we do the next one, f prime of something in there like 0. Oh, it's still negative over positive. So negative, because it's a square. Squares are always positive. So f prime of 100, again, negative over positive. It's not increasing, that's still decreasing, negative. And so if you look at our function, it should be that way. Yeah, see how it decreases to our vertical, and then it decreases to the hole, and it decreases from the hole. So that matches perfectly. So is there a local max? No, we didn't even have a critical number. Is there a local min? No, no critical number. Is it increasing? No. There's no interval for that. I'll just put none, not applicable. And it's decreasing from, and you can't say negative infinity to infinity. We have to break it up. So negative infinity, comma, negative 3, union, negative 3 to 2, union 2 to infinity. And so there we go. Oh, we forgot our horizontal and slant asymptote. And so that's our limit. And remember, our coefficients in the front are the same. So we end up with y equals 1. Let's draw our vertical line like that. I would remake the whole video and just start all over, but I don't have time, so I got to get through these. Now we need the second derivative. So we're going to take our g prime and take the derivative of this, and this time we're just going to rewrite it and use chain rule. So this is negative 2 x plus 3 to the negative 2. So g double prime would be 4 x plus 3 to the negative 3 times the derivative of the inside, which is 1. So our g double prime of x would be 4 over x plus 3, negative 3. And then no points of inflection again, because all we have is our domain. No, no, and no. That's never going to be 0. So we go back and we do the same thing we did before. Negative 3, vertical line, whole 2. And we test our second derivative. Now on this one there is a negative, I put a negative 3 there. Come on, erase 3. We do have an x plus 3 here, so we need to actually check it. And we have a cubed, I mean. So cubes are not going to make things positive. So plug in 0, 100, and so we do actually have to figure this out. But the top is positive, so we know that. We just need to look at the bottom. So if I plug in a negative, that's negative. So we know it's negative, concave down. Next one's 0, that would be positive. So we know it's positive, concave up. And then the last one is 100, so positive and concave up. And we already knew that too because it's a hole. So the hole's not changing concavity in this situation, it's just sitting there. So inflection points, no, because we didn't have any numbers that came out, so none. Concave up, yes. We have concave up from negative 3 to 2, union 2 to infinity. Yes, you do have to split it because that point doesn't exist. And then from negative infinity to negative 3, we have concave down. So now we just have to place this on our graph. And so since from negative infinity to negative 3, that is our vertical asymptote here, it's just concave down. So we know to just do this, because this is the only way we're going to get concave down. See, this would be concave up, and that's not going to happen. And then on the next side, it's all concave down. So all we have to do is make sure, or concave up, all we have to do is make sure it goes concave up, and then concave up from that point as well. And that matches our graph right there to there. So there you have it. There's a rational expression with a hole and no points of inflection and no relative extrema. Thank you.